Okay, guys. Yalla, so we'll treat together today a problem on thermal engines. Okay, so how the thermal engine can work, how we can convert heat into work. So as we discussed before, the complete description of the cycle will be provided for you, and just what you have to do is to draw the diagram and do the analysis, do the energy balance for your system. Okay, so to start with, let's say we give you the following description. We can tell you that we can model what is happening in a thermal combustion engine as four phases. Okay, the first phase will be the compression phase, and in the compression phase we'll have increase in pressure and reduction in volume. Okay, so phase one, let us write the description here. So in phase one, we can consider that we have the compression, and as I told you, we can model it as adiabatic. So we can say we have a compression that is adiabatic, and we give you the equation for adiabatic process. So PV to the power K is equal to a constant. Okay, so second, phase two, as we mentioned, what will happen after compression, we can give the spark, which will cause the ignition of the system. So in phase two, let's say, we have the combustion process. So if you remember, we said that a good way to model the combustion process is to consider that because it's very fast, it's instantaneous, we can consider that it's taking place at constant volume. Okay, so we can model it modeled as constant volume process. And during this process, you have heat input because the combustion will release heat. Okay, now for phase three, in phase three, we'll have the expansion. Okay, the expansion is one of the most important phases because during the expansion, the piston will move downward until the effect, if you want, of the push due to combustion. So it will deliver work. So this is the expansion phase through which work is delivered by the piston. And also it can be treated, yani, I will tell you, for example, here, you can treat it as adiabatic. Okay, so expansion also adiabatic. Because also it's adiabatic, so it can be treated with the same formula, PV to the power K equal to a constant. Okay, and finally, in phase four, so as we discussed last time, you need, instead of saying you have gases that you are exhausting out and you are intaking a new air, you can model this at heat rejection. Because what will happen during the exhaust of gases, exhaust gases at very high temperature will leave your cylinder, and other air at lower temperature will enter. So we can consider that this exchange is taking place at constant volume, and we can just model then this process. So heat rejection. So heat rejection at constant volume. So if I give you this description, you should be able to draw your cycle. Okay, let us try to do this together. So if we want to draw it on a PV diagram, pressure versus volume. First, they told us that the first phase is adiabatic, okay? And it's governed by the following equation. PV to the power K is a constant, okay? So it's a curve for which when pressure increase, volume will decrease, because as we can see, they are inversely proportional, okay? So we can consider, let's say, this point, okay? We can name it, here in general, one of the names used in thermal combustion engines for the point A is, for this point is A, because consider it's the beginning of admission, okay? Then we compress, so the volume will decrease, the pressure will increase, okay? In combustion books, in general, we name this point C. So I will use the conventional names, but you can select any names for these points, okay? So this is, if you want, this is phase one. This is phase one, the compression phase. This is how we can illustrate it. After this, in phase two, they told us that the combustion can be modeled as, sorry, here, constant volume, okay? So just let us fix it as constant volume. So what will happen is, because you have instantaneous ignition, instantaneous combustion process, in reality, it will take some time. But from observation, okay, in gasoline engines, it will take place for a very short time period. That's why you can consider that the increase in pressure is nearly instantaneous. And of course, the pressure will increase because the volume is constant, while the temperature will increase because of combustion. So we can consider that phase two is a phase of increase in pressure at constant volume, because they told us that phase two is at constant volume. And since we have combustion, temperature will increase, so also pressure will increase. So this is phase two. This is phase two. And we can consider phase two between 2 points. We'll name this one Z, which is the end of the combustion phase. And finally, okay, in phase three, we have the expansion. So now what will happen? Our piston first moved upward during phase one. So during phase one, the piston moved upward. At the maximum level of the piston, we gave the ignition. So we had the combustion that was at instantaneous, so at constant volume. And now, after combustion, the piston will be pushed downward. And during this phase, the pressure will decrease and the volume will increase, according also to PVK equal to constant, okay? Until reaching the dead point. So the minute, if you want, we have two main positions for the piston. It's displacing between two levels, okay? This is level one and this is level two. This is the maximum height of the piston, corresponding, if you want, to the minimal volume of the chamber here. And this is the point where we have the minimum height, okay? And we have discussed together that during expansion, under the forces of the gases, the high pressure of gases, the piston will move downward, okay? So what will happen then, during this downward motion, the volume will increase and the pressure will decrease, because they told us that in phase three, we can model this expansion as adiabatic. So here also, this is phase three. We can say that the equation of this part is PV to the power K is equal to a constant. Okay. And this is the same for phase one. They are both 1 and 3 are governed by the same equation, while rejection of heat, as mentioned, takes place at constant volume. So we have a phase of heat rejection like this. Okay. So this is phase 4. And now we want to do the analysis of this cycle. We want to know what is happening in each process, because our final purpose is to calculate the efficiency, okay? So we want to determine what is the efficiency of this internal combustion engine, okay? So let us first understand what is happening in each process to move to write the equation of the efficiency. To start with, from A to C, as we said, it's an adiabatic process. When we say adiabatic, Q is 0. Okay, so you can automatically say that Q, so Q of phase 1, okay, Q equals to heat in phase 3 equals to 0. There is no heat exchange during these two phases. Now, in phase 2, what is happening? We have the combustion. During combustion, what will happen?
We'll have a heat input.
Very good. We'll have the heat input. Okay. So we have a heat input equals to Q N. Okay. And during the heat rejection, we have Q that is getting out of the system. Now, during the compression and the expansion, if you want to do the analysis, what will happen? This system will exchange with the surrounding. It will not exchange heat, but it will exchange what? Work. Okay? Because we have seen that energy between a system and the surrounding, we can have exchange or through heat or through work. Okay? During the compression, you are putting work on your system or you are taking work from your system? When you
During
compress.
combustion,
No,
when you
I'm
compress?
telling, yeah, when you compress, during the compression, okay? During the compression phase, what is happening? You are putting work on your system. Why? Because you need an external intervention to rise the pressure, okay? That's why we consider that we are putting work on the system. And actually, this work is coming from the rod, okay? Because as your system is rotating, here your crankshaft is rotating. So it will put work to lift the piston upward. And when the piston will do expansion, the piston will deliver work to your crank. Okay? So here we have Wn. And here we have W out. And what is the useful, if you want, the useful power here?
In phase 3?
هلا مزبوط, هي the useful is phase 3, but if you want, we will one part of this produced work will go to supply input work. Power it. Yeah. Okay, yes, to power the motion of the piston. That's why in general, whenever we want to study, let's say, the efficiency of such system, we consider the network produced from my cycle. Okay, so W net in this cycle is equal to W out minus Wn. Do we have any work in phases A, B, and ZC?
No.
Why?
Because and you mean in 1 and 3?
Yes, between 2 and 4. So in phases 2 and 4, do we have a work? You remember from the course material how we defined the work? It's integral. It's integral PdV.
Of PdV.
Exactly. It's integral of PdV. Do you have any change in volume in phase 2 or phase 4?
No, it's at constant volume.
Exactly. That's why during phase 2 and phase 4, we don't have a work. Okay? We don't have a work. This is why we can consider that we have only work in phase 1 and 3. But in phase 1, the work is, we put work on the system. In phase 3, we take work from the system. So W net, the useful power, is the difference between W out and Wn. Okay, this is the useful power that I will extract from my system. And what is the input here? What is the input to produce this work?
Qn.
Qn. So if I ask you about the efficiency, how can you write the efficiency of your system? The efficiency of my thermal engine is W net over the input. And what is my input here? It's Qn. Okay, so the input is Qn. Now, let us try, if you want, to find what is W net in terms of heat exchange. If you take the whole system, it's a closed system, okay? What can you say about delta E for a closed system? You remember the energy balance, okay? If we have a system and we write the energy balance for the system, delta E is equal to what?
Zero.
Everything in minus everything out.
Very good. It's summation of everything in minus everything out. So we can say it first, it's summation of heat transfer, okay, plus summation of work transfer. Let us use the convention of plus. When we put the plus, this means anything getting in the system is considered as positive, and anything getting out of the system is considered as negative. Okay, this is the easiest convention to work with. You can work with the other one, but pay attention. If you put the convention here minus, then you consider work produced by the system as positive and work done on the system as negative. Do you have any problem with the two conventions? إذا حدا مش فاهم all conventions, I can repeat. Okay, so I will use the plus convention. When we use the plus convention, every flux or every work or heat coming in is positive, and if work is getting out, it's considered as negative. Now, what about delta E for this closed system? Look, I want to consider the whole cycle, okay? I am considering the energy variation in the whole cycle. If I consider the whole cycle, I'm starting at point C and I'm getting back to C. Do I have then any energy change if I go back to the same point?
No.
No, because I have a closed cycle. Whenever I treat a closed cycle, I don't have a variation of the energy because I will go back. I start from this point and I will go back to the same point. It's a repetitive cycle. So I can consider that delta E is equal to 0.
No,
Okay.
it's like a steady state process.
Yes, I'm dealing with steady state processes, of course, and I'm going back to the same point. Okay, that's why I can consider then that I have delta E equal to 0. And if delta E equals to 0, this means what? This means that sum of Q plus sum of W is 0. So sum of Q is equal to minus sum of W. Okay, so now let me write what do I obtain now. I have sum of Q equals to minus sum of W. Okay, as we discussed, what do we have here? We have Qn during the combustion phase. We have Q out during the heat release. So Qn minus Q out, okay, is equal to minus summation of W. So is equal to, because we have taken the term to the other side, it's minus W out minus W out plus Wn. Because we said when we do the summation of work, according to this convention, we consider positive term what is coming in and negative term what is getting out. Okay. Now, if we introduce the minus inside the bracket, so we get plus W out minus Wn. Plus W out minus Wn represent what? This is the net work of your produced by your system. So this is what you care for. Okay. So now you can say that I can calculate the net work if I just know the expressions of Qn and Qout. I can get the net work. And in general, this strategy is used a lot to calculate the work produced in a system. You can directly say that W net in a closed system, okay, is equal to sum of Qn minus sum of Qout. Here we have just one source for Qn, which is the combustion, and one source for Qout, which is the heat release. Okay. So now, if I replace back into the efficiency calculation, we said, what is the efficiency of the system? It is what we are producing actually. The useful
W
power
net.
here is W net. So we can put W net over Qn.
Qn.
Yes. And Qn, W net can be replaced directly here by Qn minus Qout. So the equation of efficiency will be Qn minus Qout over Qn. We can simplify this. Qn over Qn is 1. So we get 1 minus Qout over Qn. This is the expression of efficiency. Okay. Now what I will try to do with you, will try to find what is Qout and what is Qn, function of the parameters of our, let's say, thermal combustion engine. Okay. And then we can find an expression for the efficiency that is function of the parameters that are provided. So this is what we will try to simplify. We'll try to simplify to gather this term. Okay. So again, I will go back with you to the cycle. We said that we have the cycle. Okay. And we want to express a Qn and the Qout function of the parameters of the thermal engine. In general, okay. For example, what we give you is the following. Whenever you have a piston cylinder system, I can tell you what is the ratio between the maximum volume occupied by air and the minimum volume. So already we have considered this cycle. This is our cycle. Okay. And we said that we considered named A, C, Z, B. Okay. So one important parameter that is provided by manufacturers in general is the ratio of VA over VC. Okay. So I will give you this ratio. I will call it epsilon. Epsilon represents the compression ratio. It's VA over VC. Okay. This is defined as the compression ratio in a thermal combustion engine. So we have the value of epsilon. Okay. And plus, we know that during a constant volume process, okay, what can we say about the variation in temperature? Do you have any idea? Do you know what are the ideal gas properties?
Sir,
Yes.
isn't it proportional to pressure?
Yes,
Inversely?
exactly. So look, as I told you before, you don't have to know any of this information previously. I will give you all inputs needed. I can tell you in this problem, I will tell you, I give you the ratio VA over VC. okay? And I will tell you, you can treat air, which is the fluid here, as ideal gas. When you have an ideal gas, the ideal gas is driven by the following relation: PV equals MRT, okay? Where M and R will be constant for the cycle because R is a property of the gas and M is the mass of the gas. So these are constant, okay? So you can consider that for an ideal gas, you have that PV over T is a constant, okay? So if volume is constant also, so this is the general rule for an ideal gas, PV over T is constant. If the volume is also constant, then for phases of constant volume, you can write that if V constant, this means that P over T is constant. So you can use that the ratio of pressure and temperature is constant when you have a phase of constant volume. While for adiabatic phases, we said that what is the equation? For adiabatic phases, you can use
PV to the power
PVK
K
equal constant. Very good. Okay, so let us try together to express the efficiency. So the question will be the following: find the efficiency of your system, just function of epsilon and K. I want you to find the efficiency as function of epsilon and K. It might seem weird or hard to prove it, but if we go step by step, it's really simple, okay? Let us write back what is the efficiency. We said that the efficiency is equal to 1 minus Qn, Q out over Qn, okay? Q out is heat rejected between A and B, and this process is at constant volume. Do you remember from the course material, what is the expression of sensible heat? Can you recall from chapter 2? Yes, very good. It's MC delta T, okay? So because the process is occurring at constant volume, we say it's MCV delta T. So we can write 1 minus Q out is between points. This is Q out. It's between points B and A. So I can write it's 1 minus M times CV times temperature at B minus temperature at A. Okay, the same procedure now for Qn. Qn is taking place between which 2 points? So this is Q out here, between A and B, while Qn is between C and Z. So this is Qn. Okay, so what can we write then? We can write that Q out is Qn, sorry, is MCV. Now between which temperatures? Between points Z and C. Of course, TZ is larger than TC. So it's MCV times TZ minus TC. Okay, and now what will happen? MCV will cancel out. Okay, so the masses will cancel out. We are left with temperatures. And how can we reach this? You know, we need to incorporate epsilon and K. So here we should also think about the processes and the equation of processes. Until here, we reached this state, okay? We want to try to figure out epsilon and K. To do this, okay, the best approach, if you want, is to try to make ratios. Because whenever you have ratios, you can, for example, let's say between, as we discussed together, for between C and Z and A and B, we have P over T constant. So what can we write then? Because the volume is constant in this process, we can write that the pressure at point C over the temperature at point C is equal to the pressure at point Z over the temperature at point Z. Okay, so we can say then that the ratio of temperature between Z and C, so Tz over Tc, is equal to the ratio of pressures. So is equal to Pz over Pc. Okay, of course I am not done yet, but at least I can find expression for ratios of temperature. Because it's easy to find ratio of temperatures, let me try to simplify a little bit my equation. So here I will try to figure out ratios. Okay, so for example, in general, let's say during process A to C, okay, can I find the relation between A and C? Also yes. Why? Because I know that PVK is constant, okay, and I have an ideal gas. I have ideal gas behavior, so I can deduce a relation between volume and temperature. Okay, so yeah, I will erase this to write again. So my purpose now is to try to deal with this ratio. Okay, so I will write again. Let me open a new window. I am searching for TB minus TA over TZ minus TC, okay, over TZ minus TC. So first I will try to come up with ratios because I can find ratios from the different phases. So I will take, for example, into the numerator, I can take TA as factor because this is the initial point I started with. The initial point is TA. Then I will get inside my brackets TB over TA minus 1, okay, over. Now, because if you want, I have the first phase is between A and C, from A to C. And I want to try to find the ratio of TC over TA, okay? I can take in the denominator TC as factor. So I will get TC factor TZ over TC minus 1. Okay, so now what can I say? I can say I have 3 ratios to determine. I need to determine what is TA over TC. This is the first ratio I should look for. Okay, I should determine what is TB over TA. Okay, and I should determine what is TZ over TC. If I am able to find these factors, function of the parameters they asked me for, then I can find the expression of my efficiency in simple form. Okay, so yeah, we'll start by each of these ratios one by one. Okay, I will start with TA over TC. Okay, so again, I should think of the following. A and C correspond to which points? A and C are parts of the adiabatic phase. In the adiabatic phase, PV to the power K is a constant. But I don't need now to relate pressure and volume. Let's say I need to relate temperature and volume. Okay. Why I need to keep the volume here? Because I have the ratio of VA over VC. I know that VA over VC is epsilon. Okay. Because I know that VA over VC is epsilon, I want to try to relate the ratio of temperatures TA over TC with epsilon, with this ratio, because my final purpose is to get everything just function of epsilon and K. Okay, so I say it's true that I know that PVK equal constant, and I know that it's an ideal gas. So PV over T equal constant. Okay, so then I can say that I can replace the pressure term in my equation here. I can replace the pressure by a certain constant. If I call this constant C1, for example, I can replace the pressure by T over V times C1, T over V times C1 times V to the power K is equal to a constant. Okay, and now the constants, I can lump them together. I take the constant to this side. What do I obtain then for an adiabatic process? For an adiabatic process, I can write that the temperature times V to the power K minus 1 is a constant. So now I can get the ratio that is missing for me. So I can get TA over TCY, because if I write that TA, I will apply this relation between points A and C. Okay, so TA times VA to the power K minus 1 is equal to TC times VC to the power K minus 1. So now I have my ratio, the ratio that I need. The first ratio that I need is TA over TC. So I can write now that TA over TC is equal to VC over VA to the power K minus 1. Okay, and because I know this ratio, VA over VC, I can replace VA over VC by epsilon. Okay, so TA over TC is equal to VC over VA. VC over VA is 1 over epsilon to the power K minus 1. So this term is to the power K minus 1. Replacing VC over VA by 1 over epsilon, I got already a TA over TC, just function of epsilon and K. So I am done with the first step. So TA over TC is 1 over epsilon to the power K minus 1.